All right, well, welcome to another installation of the Chicago User Group seminar series. And again, we hope everybody's doing well and staying safe and possibly getting back to work if you're able to. I'd just like to point out again, as I did last time, the Chicago Cytometry User Group web page. So go ahead and check that out. You probably used it to register for this webinar. So again, that's chugcytometry.com. There, I'll just point out you can review these webinars that we've had. So under past events, you can view the one we had previously with Timothy Crawford, as well as keep up to date on upcoming events as well. And as we go through today, we're going to have a slide deck and a presentation. But for those watching on YouTube, go ahead and feel free to enter any questions you might have in the comment box. And our colleague, David Leclerc, will be monitoring that and feeding us questions as they come in. And if appropriate, we'll go ahead and break in while Dave is giving his presentation and ask the question. If not, we'll hold them to the end and ask them at the end. Okay, so again, my name is Ryan Duggan. I'm currently a senior scientist at AbbVie in immuno-oncology and have been doing flow cytometry there, as well as previously at the University of Chicago. And I'm joined by Laura Johnston, who is the director of the flow cytometry core at University of Chicago. She and I will be moderating this presentation, and we'll be asking questions, as we see fit. Our presenter today is Dave Novo. He is the president and founder of FCS Express, the software. So you guys are probably all familiar with that software. And just a little bit of background about Dave. He received a PhD in biophysics from UCLA. And I think mostly focusing on imaging type techniques. I think that was his preferred technology maybe during that time. But I think one of the maybe most unique or possibly unknown is that he actually worked with the one and only Dr. Howard Shapiro back in the day. So I think if any of you are familiar with flow cytometry, you're obviously familiar with Howard. And so having the ability to work with him and build instruments and do all kinds of crazy stuff, I'm sure influenced him greatly. More recently, he serves on the Data Standards Committee, which is a standing committee within ISAC that focuses on data standards. And being kind of in the software business, you can appreciate why he would be drawn to that and be an asset on that team. So today we are going to have Dave Novo here to talk to us about spectral cytometry as well as spectral unmixing. So I think it's going to be a pretty broad overview, and we're eager to learn all about this, what to many of us seems like a pretty new technology, but as you'll see, hopefully from Dave's talk, this has been going on for quite a while. So with that, I will go ahead and turn things over to Dave, who can go ahead and share his screen and please take over. Thank you.
Yeah, thanks, Ryan, for the kind introduction. Thanks for inviting me here. I really very much look forward to, hopefully in the semi-near future, actually presenting at ChUG in person. At least going to Chicago, even if you don't invite me to present, that would be really great. So I'm going to be giving a brief overview. This is really nothing FCS Express specific today. It's just a general overview on something I find very interesting, which is spectral flow cytometry, to kind of orient people as to what it's all about. But before I give this presentation, I did want to actually convey some really important information in case anybody, since we have all been living in a bubble, and as I've been reminded at least daily, It is Mother's Day this weekend. So everybody please get out and go appreciate your wives and mothers, because they're all stressed out during this period as well as us. So even if you forget my entire presentation, at least remember that important bit of scientific information. So anyway, without much further ado, so spectral cytometry, what's the big deal? What is all the fuss about? Why is it so exciting? Why is it really gone from being relatively obscure to, you know, being all hot and sexy today? And there's a lot of reasons for it. You know, there's a lot of methodological reasons and whatnot that I'm going to get that are there. A lot of reasons about the technology, a lot of reasons why, you know, the machines are cheaper, somewhat easier to set up. There's a lot of issues with that. I'm not going to be focusing on those, while they are very, very important, of course, when choosing an instrument and choosing a technology. I'm going to be talking more about the measurement side of it and the advantages and the reasons that you get from the measurements. Okay, and so what is the problem, quote unquote, with flow cytometry? I'm sure for people attending this meeting, they're obviously, I'm actually quite interested in flow cytometry and understand the basics quite well. So I'm going to go over this just very quickly. But the problem is that the dyes we use have the nerve to have wide emission bands and end up being detected in multiple detectors. So although we call this the, you know, FITC dye and the FITC detector, you can see that the FITC dye is actually spreading into both the green and yellow detector, you know, in such a way that in this little example, 500 photons from the dye ended up in the green detector and 150 ended up in the yellow detector. And similarly, if we have a second dye, which is here our PE dye, you can see again that 5 of those photons ended up in the green, 400 in the yellow, and 5 ended up in the red detector. And then similarly, when you add another dye, you see that, again, the photons that were emitted from that dye were actually ended up in 2 different detectors. And the problem is, though, of course, when we're doing the experiment, is we don't see this magical split up of the photons. All we see is this final signal, right? We just see a final signal that there were 505 dyes in the green, 505 signal or photons in the green, 550 in the yellow, 505 in the red, and 100 in the far red. And again, the signal, I'm not implying that the signals that come out of the flow cytometer are photons. Actually, they're just signals, but the principle is the same. So we get this detected signal from every detector, and we don't know how much of every detected, from each detector, how much signal came from which dye, right? And that's the classic problem we have with flow cytometry. And, you know, the real difference between spectral unmixing and compensation, or classic compensation, as I'll call it, there's not really much of a mathematical difference. It's really a difference in mindset and how people are approaching the problem, right? So how do people approach this problem with the compensation mindset? They say that an error's happened, right? You'll constantly hear that there's a problem with your machine, there's an error happened, and even from the term compensation, you need to compensate for that error, that problem that happened. And the compensation mindset is really that there's a primary detector for each fluorochrome, and that primary detector is where that fluorochrome was supposed to go if everything actually worked, right? I mean, things didn't work, so they didn't go in the spot where they're supposed to, but they were supposed to be in that particular detector. And hence even the nomenclature that's very common in the field, right? That this is the FITC detector, the PE detector, the per-CP detector. You know, it really is ingrained that there is supposed to be one detector per fluorochrome, right? And the compensation mindset is that the fluorescence is spilling from the primary detector, or the detector where it's supposed to be. It's spilling over into other detectors where it's not supposed to go, right? And so it's very similar to this, you know, instead of your neighbor's dog pooping in your yard, your neighbor's fluorochrome is pooping in your detector. And how do you go and get that poop out of your detector so you get the signal that you really should have gotten if the darn thing would have been working properly, right? That's the way that it's traditionally taught. That's the way compensation is traditionally perceived by the vast majority of people. And that's the compensation mindset, right? And so the compensation mindset is that we need to correct, like I said, we need to subtract out the signal that's spilled over from the other detectors into my detectors in order to fix the detectors, right? And I don't think, I mean, maybe some people don't understand it that way, but I think that that's the pervasive concept that compensation is understood and taught by, right? And these slides, I will acknowledge, are generously stolen from BD, who made some really nice slides in this. So what is the spectral mindset? How do you approach this in spectral cytometry? Well, in spectral cytometry, you have tons and tons and tons of detectors, right? A spectral cytometer is really nothing than a system where you have very, very many, very, very narrow bandpass detectors. And you can build that in multiple different ways. You can build that with prism to spread out the light among different detectors. You can use a grating. The detectors can be a detector array. They can be a camera you could use as to detect a spectral signal. You can actually put in, if you really wanted to, 32 or 64 PMTs, as long as they had very narrow bandpass filters. All of that would make up a spectral detector. But the point being is that you have many, many detectors, and they all sample from a very narrow bandpass. And this makes it very, very clear that there's no concept anymore of a primary detector, right? Which is in these 32 detectors, which is supposed to be the FITC detector, which is supposed to be the PE detector, which is supposed to be the PERCP detector, right? And it's obvious that there's none, right? So you've got to abandon that idea that there is a primary detector and fluorochromes are spilling from the primary into the secondary detectors, right? And so the spectral mindset is that we are going to use information from all of the detectors to figure out how much signal came from the dye, from each dye, right? It's a very different way of thinking to think, oh, I'm going to fix a detector and correct that detector so that it shows what it's supposed to show, than to say, you know what, I'm not fixing a detector, I'm not correcting a detector, I'm just going to use the values of the detectors and figure out how much dye there was. And I'm going to assume that every single detector potentially contains a mixture of photons from different fluorochromes. And our goal is to understand and understand that mixture and uncouple that mixture to figure out how much fluorochrome was on every cell. Okay, and this idea is very old. It's like from the 50s when they originally did satellite imaging, and it's the same kind of problem, right? If you've got a camera in outer space, every pixel in that camera, especially back then, was sampling from a square mile. And in that square mile, you had some trees and some water and some road and some sand. And inside that pixel, you had to figure out how much of that pixel was road and sand and water and trees. And so it's exactly the same problem in a different modality. It's a similar unmixing issue. Okay. And so what are the problems with compensation? You know, that being said, given, you know, the compensation issues that we have, you know, we have a lot of problems that come about it. And some of them are methodological, right? You've got to get single stain controls. How annoying is that? There's a lot of, you know, you might not have a lot of cells. There's a lot of caveats with what kind of controls and how often the controls and blah, 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 blah that you have to learn and understand. It requires manipulating the data after the experiment with specialized tools. It depends on the gains and whatnot. So these are some issues, both with unmixing and with compensation, actually, that make it kind of annoying. Also, there's some conceptual issues, even when you do it right, quote unquote. The data sometimes still doesn't look right, and you've got to, some people feel they have to tweak it, and how much you tweak it and when you tweak it, kind of like a little bit of black magic voodoo based on experience. Generally your core facility manager's experience and not necessarily your own experience. So you know, that's a very qualitative thing. But again, even with then, the problem, even with all of that, the problem is it still doesn't work as well as you want it to work. Even if it works perfectly, you still get these so-called spreading errors, right? And the spreading errors are very evident in this little cartoon here where, you know, in a pure world where you only had PE alone, you see that there are 2 PE peaks in your sample, in that population, but you pair that with a bright PE signal on the same cell, and all of a sudden you can't resolve your 2 dim PE populations anymore because your PE signal is red. I lost my little highlighters, not coming on this monitor anymore. But anyway, the PE signal is red, and oh, here it is maybe. So here, the red signal is with a in the presence of FTSE on the same cell. The black is without, and you can see the spreading from the FTSE dye has totally ruined your ability to resolve these dim populations. And that's really the problem. I mean, if everything else, if it just worked perfectly, nobody would really care anymore, right? So okay, so now I'm going to go on and talk a little bit about the math behind this stuff and explain, you know, how unmixing can help improve that situation. Okay, so how do these signals actually generate it? So when you have an observation from a single cell, this is what it looks like, right? You have a whole bunch of detectors. We don't really have this area over here, right? This area over here is fake. The only thing here is we have these little observations, is how much signal occurred in every detector, right? Across the entire detector array that we're dealing with. And we know that this signal that we have detected is actually comprised partially from this green dye and partially from this red dye, okay? So somehow these 2 signals added up together in some proportion are giving us this observed black signal that we're seeing. That's the theory of both compensation and unmixing. And so if we try to express that somewhat mathematically, we are going to say that our green signal times some unknown amount of FTSE plus our red signal times some unknown amount of PE, because this is the spectrum of PE and this is the spectrum of FTSE, is going to sum to this unknown signal. I mean, this measured signal, sorry. And so the goal is to figure out how much PE and how much FTSE we actually have, right? That's the mathematical problem that we're trying to solve. And so in matrix notation, which is how it's often expressed, if you turn your spectrum sideways, what you do is you get the coefficients of your matrix. All a mixing matrix or a compensation matrix is a numerical representation of your emission spectra of that dye. So you can see where the emission spectra is at its peak over here. You actually have the peak value over here. Where the emission spectrum is low, you have the low values here. So this column of a column of your mixing matrix or of your compensation matrix really is the emission spectrum of your dye as measured by your instrument. Okay? So the math is not, when you get presented with this stuff, it often looks like a whole bunch of numbers and a matrix and da-da-da-da-da, but that's all that it's actually saying. It's just the emission spectrum. Okay, so if we move that over and add our second dye, which is now our PE dye, so this is the emission spectrum of PE, and this is the emission spectrum of FTSE. Obviously, again, the emission spectra are going downwards just by convention. That's how it's typically drawn. Times the emission spectrum of the dyes times an unknown amount of FTSE and PE. this is expressed as a vector, a one-dimensional vector, is equal to the vector of abundances. And again, these, a vector that you observed. So again, this is your observation from the instrument. If you turn it sideways, you get the actual values that you observed in every detector. And you are basically just trying to solve this equation. Any questions on this so far that have come up?
Nothing on our end. I
Okay.
think digesting the matrix notation.
Yeah. So then the point of this is actually just to show that the matrix notation is nothing fancy, right? It really is nothing. It's just a numerical representation of either what you've detected in your flow cytometer from all of the detectors, or it's a numerical notation for the emission spectrum, which you measured from your single stain controls.
Yep, makes sense.
Okay. So some terminology now that we're going to use, now that we're all, linear algebra gurus over here. All of your single stain control spectra, they're called your mixing matrix. Okay, this is how your signal is going to get mixed up. These are called your abundances. What you're trying to figure out is called your abundances. These are very general terms because, of course, it's a very general problem. So in our case, we're trying to unmix two abundances, the FTC abundance and the PE abundance. And in general, FTC and PE are called end members. These are the things that you're trying to unmix. So actually, technically, the abundances are the numerical values that you've solved for your particular cell, how much FTC and how much PE. And end members are the things that that are in your experiment. And of course, on the right-hand side are your observations, what you actually observed from your instrument. Okay, if we take those away, take away all our matrices, we basically have our model that our mixing matrix times our abundances that are however many end members is equal to our observations, which is often notated by R. I don't know why R, but it is R. Okay, so that's the equation that you often see. And from some very basic math, if MA equals R, then divide both sides by M, you get A equals R over M, or A equals R times M to the negative 1, right? Because this is what you're trying to solve for, A. How much FTC, how much are your abundances? How much FTC and PE do you have on every cell? Right?
Hey, Dave.
Yeah.
Dave, yeah. No, this is great. So I was actually just reviewing your, I think it was a 2013 paper about this. So this is essentially the first paragraph of the paper going through this. But yeah, the other day when I was reading through it, I'm like, it seems simple enough, but I just can't get it. But no, now I think it's super clear. So thanks. And I would encourage you, anybody listening to, check out that paper in light of this. I think it makes a lot more sense already.
Yeah, and again, unfortunately, in those papers, we're always, as you're always asked to make it shorter and shorter and shorter. So you can never really explain anything that's not like background material. But yeah, it sometimes is a little bit brief and assumes too much prior knowledge. But so the nice thing about this, the thing I wanted to stress is so far, this, although it's probably not appreciated if you're not a mathematician, but there's really no room for spreading, right? It really looks like if you know R and if you know M, you are going to perfectly recover your abundances. So where is this spreading coming from? Where is the problem coming from, right? And I'll get to that in a moment. And so when we look at, if we look at this A equals R M to the minus 1, so this shouldn't have, I have to fix my animations here. But let's do a simple example. If we look at our little equation, if we have, this is M, our mixing matrix. And to go through it very carefully, you see that I have two dyes. These are two totally made up dyes. I have two dyes, one where 50% of that dye is going in the first detector, 30% of the dye is going in the second detector, and 10% is in the last two detectors. And I have a second dye where 5% of that dye is in the first, 10% is in the second, 15% is in the third, and 70% is in the last detector. Right, so you can imagine two spectra separated. I've got two abundances. I know that for my first dye, I've got 100 photons and 50 photons. And if I multiply those two together, this is what my observation would be. Okay, and you can trust me on that. Now, if I take the inverse of this matrix M over here, you get what's called a pseudo inverse. I'm not going to describe it. But basically, this is the pseudo inverse of the matrix. Okay. And if you multiply, if you want to say A equals R times M to the minus 1, if you multiply the pseudo inverse by your observation, you will mathematically recover your original abundances. And if you notice these two guys here, this guy, let me erase the drawings. This guy and this guy are you perfectly calculated based on your observation and your inverse of the mixing matrix. You perfectly got your result, right? No spreading, no error, everything was gotten perfectly. So again, just to reiterate that this equation by itself is perfectly reversible. And if this was the only problem, you would not have any spreading errors. You would not have any problems with compensation or unmixing. And the issue is this is actually not the only problem. And we'll get to it in a moment. We're going to do some thought experiments here. I don't know, usually I do this as a survey. Maybe do you guys have like some way for people to raise their hand in the thing or answer? All right, so we'll try to do a Zoom test here. So let's do a little bit of a thought experiment here. Assume that I have two cells that are passing through the laser in a flow cytometer. And those two cells are exactly identical in every single way. Okay, they're somehow magically exactly identical to each other. Each cell has the exact same number of fluorochromes on it. Each cell is the exact same shape. Each cell passes through the laser in the exact same orientation. And the laser power is perfectly unchanging. The laser is perfectly consistent. Everything is exactly the same about both of those cells. Okay. So my question is, and if we'll say how to do it, is will each cell emit the same number of photons if they're exactly identical to each other? And can everybody put in, let's say, a yes or a no in their Zoom meeting? Do they think that the cells will emit the same number of photons? Everything is the same or not? I'll give like 10 seconds. You guys can tell me what sort of the consensus is there if people are answering.
Is it just Ryan and I? Well, so the
David,
YouTube actually has a bit of a delay. So there's about a 20-second delay on YouTube.
Oh, okay.
Type into the chat box in YouTube. You can type your guesses there, but we'll have to take a little bit of a pause for the delay to catch up.
Is that in case I swear or something?
yeah, right.
I don't really know how to fix the delay, but it has a delay. Oh, we're getting some answers. We're getting yeses and nos.
Yeses and nos.
I think it's roughly 50-50.
Okay. All right, well then I can say confidently that roughly 50% of the people are right and roughly 50% of the people are wrong.
It's the noise.
So the answer to this is no, they will not emit the same, both cells will probably, with a high probability, not emit the same number of photons, okay? Photon emission is a stochastic event just by the nature of the physics of photon emission. And that means that there's some randomness built into how a fluorochrome emits photons from the very nature of the physics of fluorescence emission itself. What there will be is certainly you can say if 1,000 identical cells pass through, they're all exactly the same and all the caveats that I had before, on average, they will emit a certain number of photons. But this would be the distribution of the photon emission per cell, right? Every cell will actually most likely emit a slightly different number of photons. Okay, so that's one interesting point that leads to some implications later. So I'll ask another question. Okay, so we already know that each cell emits a different number of photons. So my question is, of the photons that are emitted for each cell, so let's say a cell emits, in our little example, the cell is emitting 1,000 photons on average, but we know that sometimes they'll emit 1,004, they'll emit 998, they'll emit 920, 1,050, whatever they'll emit. Will those emitted photons be distributed according to the emission spectra of that dye in the same way? Okay, so will those 1,000 cells, will the emission always obey the emission spectra? Even though the cell may be perceived as being slightly brighter or slightly dimmer, if we know that this is the FCS emission, will every cell emit according to the FCS emission? And that's our next skill testing question.
Type it in the comments again. We'll see. I think we're about caught up, almost. No answers yet. Oh, we've started.
Is this on the certified cytometrist exam?
This is, I haven't gotten it approved yet.
Okay.
So what's our consensus on this one?
Roughly 50-50 again.
Oh, man.
Roughly 50-50, man.
Make up your mind, people.
These cytometrists are a wishy-washy group of people. So the answer to this question, again, oops, let me clear my drawings here. The answer to this question, again, is no, okay? Not only is the number of photons emitted stochastic, the actual distribution of those photons that are emitted are stochastic. So on average, the cells will emit according to an average emission spectra, but every individual cell will actually have a very slightly different emission. Okay, and you can see here, this is two individual cells, one in green emitted by pure luck exactly at the average emission spectrum, and another one more typical, actually emitted slightly off the average emission spectrum. Okay, so we've got two sources of randomness. One is the number of photons emitted from seemingly identical cells. One is the emission spectrum by which they emit from two seemingly identical cells. Okay. So what are these random distributions? So these random distributions follow the Poisson distribution. This is a very ancient distribution, and it is one that you obtain when you count things that happened at an average rate over a certain interval. Okay, so to make that more concrete, let's say you were standing and watching the number of cars enter a parking lot over a 5-minute period. In the first 5 minutes, there'd be 30 cars. And in the second 5 minutes, there'd be 27 cars. And in the third 5 minutes, there'd be 33 cars. If you kept adding it up over lots of 5-minute periods, you would get an average value. The average would be maybe 32 cars every 5 minutes. But there would certainly be a distribution. It's not like every 5-minute period, exactly the same number of cars are coming. And if you actually mathematically analyze that distribution follows the Poisson distribution. And there are a lot of things, and again, it's a very general, right? As long as something happens at an average rate, where that rate is changing, but there is an average, and you count it for a certain interval of time, you will get a Poisson distribution. So things that you're very familiar with, cars entering a parking lot, if you actually count the number of raindrops hitting a puddle in a certain period of time, the number of people exiting a train station over a certain period of time. This was actually developed by the number of soldiers kicked by horse kicks every year. And also more relevant to us than horses, the number of photons emitted by a molecule in a certain period of time, and also the number of photoelectrons created in the amplification stage of the dynode array inside the photomultiplier tubes also obey Poisson statistics. Okay. I will save you the pain of deriving it and showing how it works, but I will go to the main point that the key interesting thing about the Poisson statistic is that the variance of your distribution equals the mean. And what does that mean is that the more counts you have in a particular period of time, the more variability you will have in those counts. Okay, so what that means is that the data is noisier. You're going to have a wider variability up here. If you look at hundreds and hundreds of cells, you're going to have a wider variability up here than down here. Okay, this is opposed to a Gaussian distribution where you have a variance, and if it's Gaussian noise, the variance is the same no matter what the magnitude of your signal is. Okay, that's the key thing of the Gaussian versus a Poisson. Okay, and so if we look at some real data, here's some real data from a bead, from a spectral cytometer, just some beads. And if you look at the spectrum, you can see that this is the spectrum of these single stained controls, right? And you can see that at every point there's a variance, right? So when we say that there is an emission spectrum for these particular beads, that really means that we're measuring an average emission spectrum. But here is actually, you can see in every channel, there is a spread from these beads that are all seemingly identical. You can see how tight they are over here. These are very tight population, yet there's quite a spread. And you can say, okay, well, you know what, that spread is actually because some beads are bigger and some beads are smaller, and maybe there's two beads, maybe the blah, 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 blah. This is not a perfect experiment, right? So that's what's the cause of this variation. But actually, if you normalize the beads such that in their brightest channel, they all have the same value. So that will take into account that some beads might be a little bit brighter. The beads that are brighter, I'll make them a little bit dimmer. The beads that are dimmer, I'll make a little bit brighter. I'll scale everything up so that at their peak, they're all the same. So if there were two beads, if the bead got absorbed a little more dye in the chemical process, that will be taken care of. And you can see that still there, even if though it's normalized up here, there's still a large variation in the other detectors. So that you can normalize one detector, but because the noise is random, that normalization won't apply for all of the other detectors. Okay, so you still get noise in all the other detectors. Again, underlying the fact that the emission spectrum that we are measuring and that we're saying is our single stain control emission spectrum is really an average emission spectrum. Every bead or cell emits slightly, ever so slightly differently. Okay, so if we go back to our math now, we said that R equals MA, and remember that MA is a mixture of the emission spectrum obtained from the single stain controls. Well, let's qualify that. What we really have is M is the average emission spectrum from the single stain controls, all right, based on the discussion that we've had. Okay, so remembering that your mixing matrix is simply an average, let's ask the question, what happens if we unmix a cell that did not emit according to the average emission spectrum using the average emission spectrum. So again, to sort of repeat that, let's say we have a cell and we know that the vast majority of them don't emit on this average emission spectrum. They're ever so slightly different. But when we unmix them, we always unmix with the same mixing matrix, the mixing matrix being the average. So what happens when we do that? Let's walk through a problem. So if we have two dyes where the two dyes, dye 1 and dye 2, we're only going to do a 2-detector system to make it easy. The first dye emits 80% in detector 1 and 20% in detector 2. The second dye emits 30% in detector 1 and 70% in detector 2. All right, simple problem. And we know that our dye 1 is brighter than dye 2. Dye 1 emitted 5,000 photons and dye 2 emitted 500. Well, if we take cell number 1 emitted exactly according to the mixing matrix by some magic, by some luck. And some of them will, right? Statistically, there will be a few cells that emit exactly at the average value. In that case, dye 1 would have emitted 4,000 photons here and 1,000 here, right? Because it's 80 and 20. Would have emitted 150 of the 500 here, 350 there because it's 70 and 30. And our observation would have been this value. This is what we would have observed in our flow cytometer. Now let's take cell 2. Cell 2 emitted slight deviation from M, and I picked values that it deviated by that are absolutely, theoretically, and practically feasible and possible. And you'll see that instead of 4,000 photons, instead of 4,000 photons in detector 1, it actually emitted 3940. So it emitted a few less of those photons in detector 1, a few more in detector 2. And the other dye, dye 2, also emitted a few more in detector 1 than the average would have, and emitted a few less in detector 2. Not by much here. You can see 10 photons less, 10 photons more, not a huge difference, right? In that case, the signal that we observe is 4,100 and 1,400 instead of the average value, which we would have observed 4,150 and 1,350, right? If that happens, and then we unmix them with our mixing matrix, you see that if we unmix it with the perfect mixing matrix, with the average mixing matrix, and it emitted according to the average mixing matrix, we get back our real result, right? We recovered 5,500 right away. But if we actually take the cell that didn't emit according to the mixing matrix and unmix it with our mixing matrix, then you can see our results are totally off to the point where we actually are calculating that we had a negative amount of dye 2. So even slight deviations from the average mixing matrix can yield very strange results when you unmix with the average mixing matrix. Okay? So,
hey Dave.
Yeah.
Just before we go on, there's a couple of questions. So the only difference then between the simple example with 2 dyes and say like spreading things over lots of colors and lots of detectors and lots of lasers is just more rows and columns of data.
Correct.
So that's not
it doesn't impact the theoretical understanding at all. Yeah,
correct,
it's just more, it's really more, in terms of the mixing matrix, it's just more columns of data. Every N member, every dye you use is typically a column in the mixing matrix. And if you have more detectors in your system, it's a different row. So it's more or less rows based on the number of detectors and more or less columns based on the number of N members, but the math works out the same.
And then I mean, I don't know if you're planning to get into this at all, but the adjustment of like a voltage or a gain where you're actually moving things up and down the scale, does that impact this?
Not really.
Yeah, right.
No, not particularly. I get into the math why, but as a ballpark, this doesn't really impact this at all.
Okay.
So for those of you who are often wondering why you get negative values after unmixing, just remember this little cartoon over here, and I'll discuss it a little more as we go forward. So what happens when we unmix a cell that did not emit according to the average mixing matrix, and we unmix it with the average mixing matrix? We get spreading. Okay, that's the result of, that's what causes spreading. So if we have a generalization of our model, we had before that our observation equaled our mixing matrix times our abundances, but now we're going to add more correctly noise, all right, plus a little bit of noise. Now, what is noise? And again, I want to do that because, you know, there's been talked about that there's noise in sort of the past in compensation. And then it's been explained as, oh, this noise is dark current from the flow cytometer. This noise is stray light from the air. This noise is fluctuations in the laser voltage. This noise is electronic noise. There's all sorts of noise, and that's what causes the spreading. Those sources of noise do exist and do make matters worse. But even if you have an absolutely perfect flow cytometer in a perfectly dark room with the most expensive laser, and everything there is, the electronics are cooled to -200 Celsius, so there's no noise in your electronics, you will still have noise. Because this noise in this mathematical model is defined as the difference between the average mixing matrix and what your cell actually emitted. And since the cell, by the nature of physics, always emits randomly, by and large, every cell will have a deviation from the average mixing matrix. The spectra by which the dyes are emitting will deviate from the average value from those dyes, and that's what this noise is. You can add on as many other noises as you want to make matters worse, but you can never take away this noise from the system. Okay, not in this universe anyway. And so where your model really is not that A equals R over M. Your model is really R minus N over M, right? That's the real world model that we're dealing with. Okay. And the point is, though, is that we often forget about it. When people did compensation, and in general, when people do unmixing, they kind of ignore the noise. They run compensation in particular, you can't do anything about it, right? So you unmix or compensate with the average mixing matrix, and you ignore this noise that's there, the deviations from the average mixing matrix. But like it or not, the noise is actually still there. And the M term in this equation ends up taking this noise and spreading it all throughout your measured abundances. So your calculated abundances, sorry. So your calculated abundances are not only the real abundances that you want to get, they're also comprised of the noise that was in your system, i.e. the deviation that those cells happen to make from the average, spread out according to the mixing matrix into your final measurement. And that basically spreads out the signal over large numbers of cells, if you're graphing large numbers of cells. Okay, so if you forget about it, that's what you get. But that's not even the worst of it. The worst of it is, in this case, the noise is Poissonian, right? If we remember. What that means, again, is that noise in this part, it's noisier in absolute terms in this part than in this part. And what happens is that unmixing tends to move, or if we want to say there's larger deviations on a cell-by-cell basis from the average in this area in absolute terms than there are in this area. And unmixing tends to move the noise from the detectors with lots of photons to the detectors with less photons. All right. And just the way the math works out, that spreading works against us. And so what happens is that the dimmer signals and the dimmer detectors end up getting proportionately a lot of noise from the brighter detectors, and that helps make our problem worse when trying to detect dim signals. Okay, so I'll just give a summary and then take some time for questions. So what did we learn? We learned that fluorescence emission from cells is stochastic, both in the number of photons and in the emission of the fluorescence. The absolute noise, the difference between the average and what a cell actually will produce, is the highest in bright areas where the signal is brightest. This difference between the average and what you actually emit is the noise in these equations that we're talking about. And unfortunately, and again in summary, the pattern of emission, the way every cell emits, is different from every cell before, yet we're always unmixing with the same mixing matrix, exactly the same mixing matrix, even though every cell is different from every other cell. And so that becomes our problem. So any questions on that before I quickly go into the last part, which is how unmixing may help us solve this issue or improve this problem? I guess we have to wait a few seconds for people to type any questions.
We haven't had any as you were speaking, or I think we've covered the ones that have come in so far. We can give it a few seconds to see if there's.
Yeah, just one came in now. I'm reading it as Dave is typing. It's basically saying, can you give different weight to channels to better resolve fluorophores?
Yeah, and we can, well, I'll address that at the end. The answer
Okay.
is yes, although it again becomes challenging to determine what weights are appropriate and what weights are going to help and what weights are going to hurt, given the system you have and the dyes that you have, right? If it's just a 2-dye system, it's somewhat easier. If not, it becomes that. But yes, that's a common strategy.
Okay.
So how does unmixing help us? All right. So I'm going to go back to a little bit of math again. So we're basically solving this equation, right? Unmixing is basically solving this system of equations, as is compensation, actually. There's not really a fundamental difference between them. The fundamental difference is here. If the system is full rank, if you have a system of equations, you have the same number of unknowns as equations. And there is a unique solution to this problem, right? There's only one answer. If you have the same number of equations and as unknowns, it's called a full rank system, and this is there's a one solution. And this is compensation, right? Compensation has a square matrix. You have 5 detectors, you have 5 dyes, same number of equations as unknowns, and you always have one result, okay? An overdetermined system is one that is more equations than unknowns. That's our unmixing, that's our spectral cytometry. We have 32 detectors and 5 dyes, so we have 32 equations and 5 unknowns. And actually, generally, there is no solution to this problem, and I'll explain that graphically in a moment. It's called an inconsistent system. And an underdetermined system is less equations than unknowns. There's an infinite number of solutions to this, okay? And I'll show that graphically here in the next slide. It's not as complicated. So if we look at an underdetermined system, if we're just solving for y equals mx plus b, everybody's familiar with that. And we have 2 unknowns, m and b. And if we only have one data point, then there's actually an infinite number of solutions that you can solve for m and b that will pass through this data point, right? So that is an underdetermined system. We have 2 unknowns and only one equation to solve it with, one data point, okay? If we have a full rank system where we have 2 actual values, 2 equations, then you can see there's a unique solution. There's only one solution for m, one value for m and one value for b that will pass through both of our data points, right? So that's a full rank system. That's our compensation system where we have a single solution. And if we look at an overdetermined system, we have a lot of data points and there is no single solution at all to a value of M and a value of B that will pass through all of our data points, right? This is an overdetermined system. We have, unless you're in some very special case where they all line up exactly on the line, you are in a very, very case where there is actually no solution to the problem. And that's where we are in unmixing. There's no unique solution or no solution. And if there's no solution, how do you pick the solution? And so it's like the two rabbis arguing, well, if there's no solution, how do you pick the solution? Well, you choose the best solution. Well, how do I know which one is the best? Well, the one that fits the data the best. But what if my data has noise? Oy, you're giving me a headache, right? So it's a really semantic argument. What is the best? It's, even though it's math, right? What is the best from one point of view is not the best from another point of view, right? And so the kind of general way we do the best is we do our linear regression and find a line that kind of goes through the middle. And mathematically, what they're doing is that we're picking a solution that minimizes the total distance from all of the data points to the line, right? And the implicit assumption behind our standard linear regression that we do is that in each measurement, the uncertainty of the same is the same. And therefore, the distance from every point to the line is just as meaningful no matter where it is, right? So graphically, what that means is we are picking a spot, we're picking a line where the sum of all of these black lines is minimum, right? We're trying to draw a line that has the minimum total distance from the curve that we generate to all of the data points we're trying to fit. And again, what that means implicitly when we're doing that is that the length of the black line here, where we're at a high value of X, is the same meaning and the same importance and the same relevance as the length of this black line here, where we have a low value of X, because the uncertainty is the same. And that's our kind of Gaussian assumption. But that's not necessarily the best solution for flow, because we know the uncertainty of the measurements gets higher the brighter the signals get. And the certainty of the measurements is better in an absolute sense. The absolute deviation is expected to be lower in the areas of lower signal. So here, deviations from the fit are less impactful. Here, deviations from the fit should be more impactful. But with the Gaussian solution, deviations from the fit are impactful no matter where they are, with the same impact, right? So what can we do about this problem? And this goes back to the paper that there's a more detailed mathematical treatment of this problem in the paper that Ryan mentioned that we wrote, Bartek and I wrote many years ago. When you're doing compensation, you can't do anything, because in compensation, you're dealing with a full rank system and you just have one solution, and that one solution exists no matter what. You can't do anything with it, right? But if you have more detectors than unknowns, the unmixing problem can be understood as a multiple regression problem. And with multiple regression problems, you can apply various different regression models. The mathematical world is not limited to linear regression. There are lots of other ways to fit curves aside from the standard linear regression that you're used to. Okay, and because we have more detectors than dyes, we can use these more advanced techniques to apply different models to the data. Okay, and we can use a noise model that is somehow more appropriate for flow cytometry data than a simple linear regression. And in that paper, we talked about, here's the reference to it here. We simulated, this is from a simulation, but we simulated data that had a double positive and a single positive and a single positive. This is the raw data values that we somehow magically simulated. And then we mixed them together and we used different unmixing models. We simulated them together, we mixed them together and added realistic Poisson type noise to the model. And when we unmixed it using the standard approach, which is a Gaussian type unmixing, assuming a Gaussian noise. And remember, we just had a model where we added Poisson noise and we're unmixing, assuming Gaussian noise. You can see the spreading of the negative populations compared to what we had. And then this bottom one is when we chose to use regression strategies that more appropriately account for the Poisson nature of the noise, we recover the original signal much better. Okay, and that's as much as I'm going to say about that. The paper is 10 pages just talking about basically this one point over here. Okay. So why, again, to recap, why does spillover spreading happen? It's all this guy's fault. There's nothing you can do about it. There's nothing you can do to your instrument. There's nothing you can do to your light sources. There's nothing you can do to completely eliminate this problem. And so why spectral cytometry is so cool from a data analysis point of view, never mind all the other stuff about the cost of the instrument and the ease of cleaning and this and that and whatnot, is really, it allows you to apply more sophisticated models to your data to more accurately unmix the abundances that you're trying to get than you can with just a simple compensation system. And then not only that, again, you know, so Sony at the last Cyto pre-announced, and I have no idea where they are in the process, but they pre-announced a cytometer with like 100 or 200 detectors. I don't remember the exact number. You know, currently there's about 30 or so in the current generation of Cytec and Sony instruments. You know, but certainly once we get to hundreds of detectors, there's a wealth of mathematical tools that we can apply to the data that is gonna, you know, in Star Trek days, people are gonna laugh at us that we did compensation, you know, way back when in the day, because just the mathematical tools that'll be available are much better, much more sophisticated. Okay, so thank you for your attention. And I do want to, again, stress that this presentation also was put together with a lot of help from Bartek Raiva, from Purdue University. He's a friend and a colleague and also a world expert in this type of stuff. And I really appreciate his input as well.
Great, thank you. That was awesome. Yeah, I think we have a few questions that have come through.
Oh, so to let me address the weights issue again.
Okay.
So, you know, weighted least squares is something that we did in the paper. It's a tried and true, well-known technique. It does, with appropriate weighing, improve the results, or can improve the results you get from unmixing. That being said, you know, the weight selection is critical, and there's different weight selections will result in different results. And just because you say that it's weighed, it doesn't mean that it's weighed correctly or weighed appropriately. So you have to, you know, just because someone says they're using weighted least squares, in and of itself doesn't mean anything until you know how the weighing was chosen and why it's chosen and what it's doing to your data. But yeah, that is one of the more sophisticated techniques that can be applied.
Awesome.
Definitely got questions coming in right now. I guess we're a little bit over time, but I think most of the people are staying on for now, we can take some time to answer questions. And again, this link will remain if you want to come back and watch the recording of it. It's the same link on YouTube, or you can find it on the ChUG Cytometry website. So I guess one of the questions is, when we were talking about noise, is the level of noise related to the wavelength of the detectors? So I guess, did that higher wavelength detector?
No, I mean, that might be any additional noise in the photomultiplier tubes. Certainly, certainly the red detectors have historically had problems compared to the blue and green detectors, both in terms of sensitivity and noise. But even if you had perfect detectors, This type of noise is not related to the wavelength. It's more related to the number of photons that would be emitted in any given wavelength than to the wavelength itself.
And then I don't really get this question, but you might understand it better. But essentially they're saying, or have a comment that R in your equation has some distribution and M has some distribution. So does that mean that our reference control also contributes to error? I don't know if you can
So in
tease
the
something out of that.
equation itself, R, you can look at R as a matrix where it's the observations from multiple cells, in which case R would have a distribution. However, R is also is an observation from an individual cell, right? So in which case it is just a concrete observation that you're trying to unmix. That being said, your single stain controls, your reference controls definitely do have a distribution. And that's one of the potential, and again, we're ignoring that distribution, right? We're just taking the average mixing matrix from those reference controls. So ignoring the aspect that your reference controls may not have even the same characteristics as your cells. For example, if you are getting your single stain controls from beads and then you're applying those to cells, certainly the distribution and characteristics of the fluorochrome are very rarely exactly identical. But even ignoring that, certainly the single stain controls do have a distribution. That distribution is being completely ignored in the current unmixing process. It might be a very interesting thing to try and use that measured distribution as some sort of surrogate of the noise model. The problem is, the question is the distribution that you measure on your single stain controls useful or indicative of the distribution of the emission of the fluorochrome on your cells? Right? And that would be an unknown. And again, if you do figure out a way to apply or use the distribution from your reference controls, is that making matters worse or better if your cells don't have that same distribution? I don't know.
Yeah, I mean, there seems to be a couple of questions regarding noise and sources of noise. So let me just try and sum up a few of them. Maybe we'll take them all out together. So, you're talking about a specific type of noise, comparing each event's deviation from the mean that's created from the reference. But, you've referenced other types of noise. So part of the question is, what's the magnitude of the noise that you're talking about compared to these other sources of noise? Is this a major source of noise or a minor source of noise? Should we worry about other things more so than this? And then along those lines, would something like using a PMT versus an APD lower some source of noise there that would contribute to better resolution all around?
So it's really hard I mean, it's a great question. That's a really great question. And it's really hard to answer without knowing what instrument and what exactly it is that you're measuring, right? It's hard to say in general. I can say that even if you do perfectly remove all other noise sources, you will still have this noise, and this will give an impact on your data. You saw that spreading in the simulation a few slides back. This is a very, very realistic simulation where the only noise source that exists is the mixing and the Poisson noise. There literally is no other noise source mathematically. And you can see you already observe this. Other noises are just going to make it worse, right? If it turns out that your red channels are way noisier than your blue channels, it's going to add an additional source of noise to your signal. And then when you unmix that noise is going to spread all over the place. If it turns out that your electronics are nonlinear and they're noisier in one amplification part than one part of the range than the other, again, it's going to make it worse. So it's hard to say what is the most important source. And I'm also not going to get into the PMT versus APT debate because there's no single answer to all of that either. So it's a very long-winded way of not really directly answering the question, but saying that, they're all important. And this source of noise, the baked into the physics source of noise, is certainly biologically relevant. And certainly the fact that you can use different models to unmix real flow data and get better results. This is just a simulated model up on the screen, but we have done it on real data, and you get better results with more sophisticated models, indicates to me that this type of noise is significant in today's modern instrument, in spite of all the other noises that are there too.
So do you, I'm, sorry, I don't even know the answer to this question, but do you know whether the instruments that exist today are using the proper unmixing algorithm, like employed by different companies?
I wouldn't say that there's proper, because I don't know that there's one. Some of them use ordinary least squares. Some of them, I think, use ordinary or some version of weighted least squares. I don't know what is proper or what is not, right? I don't think it's settled what is the ultimate way of analyzing. And to be honest, it may be completely irrelevant for you, right? Like if you're not trying to really get super quantitative results from very dim populations that are expressed in the presence of bright populations, people did compensation forever, and compared to the stuff you can do here, it's super crappy, but people got a lot of nature papers out of compensated data as well. So, a lot of it also, in general, it's better to do unmixing than compensation. You're never going to get worse results just because you have more data. Even the worst kind of unmixing will still give you better results than compensation, except under certain very, very degenerate made up circumstances that, you could contrive something, but they don't really happen in real life. To give a precise answer to endorse one product versus the other is, I'm not gonna do that because they have better unmixing or worse unmixing. It's only one component. Certainly, I will say FCS Express in a very short while will let you choose among many different unmixing models, and you can see the impact of them on your data. Right now, we do only have ordinary least squares for various reasons.
Okay, awesome. And I think another interesting thing that's come up here is where does autofluorescence fit into this model, especially if you have multiple cell types with different autofluorescence? Like, do you just treat that then in essence as another fluorescent marker?
Yeah, that's a super, super question, because that's something I didn't touch on it here, but that is another real benefit of spectral unmixing, right? In compensation, there is no way of dealing with autofluorescence because you don't really have a detector for autofluorescence where you're detecting the autofluorescence and you can unmix it too. So basically, if you read all the papers about compensation and autofluorescence, there's a lot of hand waving going on that essentially boils down to just ignore it because it's not really very important. And hopefully your signal's brighter than that. And, it's understandable because there was nothing you can do about it. But with spectral unmixing, you actually can, since you have an overdetermined system, and you can, if you've got a 32 detector system, you can unmix 31 species. And so your autofluorescence is just considered another species, right? And it has its own spectrum, just like a fluorochrome. And if you have multiple autofluorescent species and you can somehow measure average spectra for them, you can have them as multiple fluorochromes in your system. Not all software allows you to do that. FCS Express does. And then you can unmix them just like any other. Now, how much will it help you? It really does depend on how abundant those autofluorescences are compared to the samples you're trying to measure, right? If you're really trying to measure only bright signals and your autofluorescence is 10,000-fold less, it's not going to make a difference, right? You won't, unmixing those will not change anything. But if you happen to be trying to unmix signals that are maybe only twice as bright as your autofluorescence, then correcting for, and especially if you, if the autofluorescence is different on different cell types, and you're trying to get a value for some antibody that is present on a cell population with a very bright autofluorescence, and maybe your antibody is only twice as bright, is 3 times as bright on that cell. Maybe on another cell, the antibody is 50 times as bright, but on that particular subcell or cell population, it's not. Then having the accurate autofluorescence signature and incorporating that in the mixing matrix will definitely be critical. And I mean, there's been a couple papers that showed that unmixing autofluorescence is possible and useful already.
Mm-hmm. Yeah. Yeah. And then speaking of like a overdetermined system, so is there a point in which you have split up the spectrum into too many bits? Like, you know, you have, like you talk about the Sony, I think it's their ID 7000 that has, you know, hundreds of detectors. Is there a point where you're going to split up so much that, you know, your detector is not sensitive enough maybe to pick up such few photons, you know, per detector? Is that a thing? And do you have any idea of where that limit might be?
Yeah, no, so it's a really good question, because if you actually do this in a pure mathematical system, you can split the signal up as much as you like in a pure world, to the point where there's like 1 photon per detector, and still accurately recover your abundances, okay? However, in the real world, detectors do have a baseline level of noise. And most detectors in a flow cytometer are not going to be the level of noise that they have. You will need to have a certain amount of signal to accurately measure the number of signal in that detector. So if they had amazing detectors that had no dark current, or had like 1 femto amp of, I don't even know how they're measured, but 1 tiny, tiny amount of noise, and I have seen some detectors, some specialized detectors that are single photon counting detectors, for example, you could split it up a lot. Practically speaking, you do have to get above the noise floor of the individual detectors. And if the noise floor of if the noise of the detectors is the same order of magnitude as the signal you're getting, because you're getting such a low signal, you definitely will split it up too much, quote unquote. To say when that will happen, it's impossible for me to say in advance. I would presume that if you're going to build an instrument with 250 detectors, that you validated that those detectors have little enough noise that for biological purposes, the number of photons you get in them is above the noise floor of those detectors, I would guess, to give them people the benefit of the doubt.
Great. I think there was one more question.
Yeah, I think there's one last one. So
yeah, one more.
Explaining when you have 2 dyes that are very close to each other. So I guess an example would be like FTSE and BB515, or BB421 and Pacific Blue. Can you explain why there's more spreading with those?
Why there's more spreading those with what, in under normal circumstances, or just in general?
I guess if I'm interpreting the question correctly, why like Pacific Blue and BB421, which are highly overlapping, have a lot of spreading, unlike BB421 and APC.
So one way of thinking about it, it's not 100% mathematically correct, but it's somewhat mathematically correct, is that the way the algorithms work is that they try to find, if they find unique detectors for a particular fluorochrome. For example, what I mean by unique detectors is that there are detectors that have emission into those detectors as measured by your average mixing matrix only from one fluorochrome, let's say in the best case, the algorithms can use that single detector, like it tries to use all of them. But if it finds that there's one that really is only from a single fluorochrome, that detector becomes very important in the unmixing process, essentially, for figuring out the abundance of that fluorochrome. So if the dyes are separated from each other in certain ways, there's lots of detectors that are unique to one dye or the other, if we take a simple 2-dye experiment. And so the algorithm doesn't end up using the detectors that are highly overlapping for both dyes don't end up being as important for discriminating and calculating the abundances as the dyes that are unique for each one of the signal. If you take 2 dyes that almost all overlap, there's really no detectors that are unique to any signal. And so the noise, it's hard for it to know what's really signal and what's really noise. And again, remember, the mixing matrix ends up spreading the noise from bright detectors within a dye spectrum to dim ones. But if the bright signal from a dye spectrum, if the dim signals from that spectrum are already not even overlapping with your other fluorochrome, then even if it moves the noise, it's trying to move the noise around and do stuff, that noise is not getting moved into the other fluorochrome because the other fluorochrome doesn't have any emission in the, or very little emission where the first dye is. But if they're highly overlapping, the algorithms can't figure out as well which noise is from one, which noise is from the other, how to figure out the abundance. It's a very like non-mathematical explanation, but it's the way I first understood it.
That makes sense to me.
Yeah, still want to separate our spectra.
Yes,
whenever
absolutely.
possible.
Absolutely. And it actually is kind of amazing that even, even with a 32 detector system and people are pushing it with 24 color panels, there are no detectors anymore that are unique to any dye. Like they all have signal from multiple dyes. But the algorithms work amazingly well. Like even ordinary least squares, like it works amazingly well by and large. And I'm constantly surprised by that somehow.
Awesome. Yeah, no, I think this was great. A lot of great information for us to kind of ponder and jump off from here and learn some more about all this stuff. So thank you, Dave, for going through that for us. Thanks also to everybody who joined in live and provided all those excellent questions. Those weren't my questions. I was just parroting what you guys were telling me to say. So thank you for the excellent questions. I think it was really beneficial and allowed for us for a greater conversation. And I would also just plug, the ChUGcytometry.com website again, so you can join the forum. We can keep the conversation going there. It's hopefully a way that we can have these discussions even in between these seminars that we're doing. And just because we're the Chicago user group doesn't mean that you have to be in Chicago to join and be a part of our little get together here. So please share it with your friends and colleagues, and we hope to see you online. So again, let's give Dave a virtual round of applause for his work. Excellent. And special thanks to David Leclerc, who is manning everything on YouTube for us, getting us those questions, and for Laura helping to moderate this session. Dave, before you go, if people want to reach out to you directly, is there a way for people to get in touch with you?
Yeah, I mean, you can just email to me. It's David, david.novo @denovosoftware.com, DENOVO software.com. And again, as a mild, something we are going to do forward more and more and more is incorporate a lot of these cutting edge techniques into FCS Express. And we're already working with some partners to try and analyze interesting data sets and see, practically where does this help. It's all nice and good that it helps in the cartoon simulation in this paper and the data set that we found for that. But now the data sets are much more sophisticated than they were, 5 years ago or 7 years ago now. Man, I'm getting old. So if anybody does have some interesting data that they think would benefit and want to try, again, just reach out and we'd be glad to look into it.
Yeah, and I'd encourage you all to visit the De Novo software website, which I'm pretty sure is just denovosoftware.com.
Mhm.
And you can learn more about FCS Express and all the software tools they have to offer as well. So with that, we will sign off and hopefully see you again on another webinar shortly. But before that time, please do check out chugcytometry.com. Thank you and have a good day. Say again.
The description box. If you need the direct link to the forum website, it's in the description on YouTube.
Great. Thank you. Bye-bye, everyone.
Thanks.